I'll share my screen. There it is. Fabulous. All right, so now what we've been doing is talking about quantum gases. And so we've talked about a Bose gas. Okay, and so that's a collection of bosons. And what we showed is that when the density gets high enough, either as a consequence of adding more particles or by decreasing the temperature in such a way that the particles all condense, that what happens is that at some critical temperature, which I believe we called TBEC C for the critical Bose-Einstein temperature, you get Bose-Einstein condensation. Man, that's a lot of dashes. Okay, and what Bose-Einstein condensation is that essentially the the average occupation number of the ground state uh, diverges and heads towards infinity, and so all the particles are starting to collect in exactly the same quantum state. Okay. Last lecture, we tried talking about a Fermi gas. And what we showed was that Fermi gases behave in essentially exactly the opposite way, that you can lower the temperature in order to try to, suppress the amount of energy in the gas and the amount of, uh, um, suppress the total amount of energy in the gas by lowering the temperature. And what we showed is that even if you do that, even if you're able to get the temperature down to 0, that the gas will still have pressure. And the reason for that is, again, essentially exactly the opposite of Bose-Einstein condensation, is that even without any external input of energy, they hate each other so much that they avoid each other, and as a result, exert this what's referred to as degeneracy pressure. So you get degeneracy pressure even at T equals 0. Okay, and that again is a consequence of the Pauli exclusion principle and the fact that you can't get all your particles down to 0 energy because they refuse to be in the same state. All right, now before, I promised you last lecture that today we were going to move on to the Ising model, but before we do that, I thought I would talk about one last thing regarding quantum gases, and we're not going to do any math. I'm just going to essentially describe for you qualitatively how it works. And that is something of a combination of these two things that shows up in the context of superconductivity. Okay, so superconductivity is when you have a material that you apply a voltage across it, and the resistance of that material goes to 0. All right, so the resistance R goes to 0, again, past some critical temperature. And so again, so what happens is essentially you get free flowing current with no resistance. Okay, and now you may recall from your introductory physics classes that current refers to the flow of electrons, right? Okay, and electrons, as we know, are fermions. Okay, but now it turns out that superconductivity is actually a consequence of Bose-Einstein condensation. So superconductivity arises because the electrons Bose-Einstein condense. And you say to yourself, Professor Kuhlman, have you gone mad? They're fermions. They can't Bose-Einstein condense. What the hell is wrong with you? And the answer is that there's actually a rather interesting little mechanism going on. And so at the beginning of last lecture, we talked about phonons, right? So phonons are the elementary excitations of the crystalline field of a material where the nuclei of the atom or the nuclei of the material is arranged in a crystalline fashion, and then when you excite vibrations within that crystalline lattice, they act like bosons. Okay, and so now it turns out that what happens with superconductivity is that there is actually an interaction between the electrons and phonons that lead to a pairing of electrons. Okay, so what happens is essentially that you've got two electrons zipping around inside your conducting material, and what happens is that those two electrons pair up with one another, and because each of those electrons has spin a half, when they pair up, they form a composite particle. Okay, and so this composite particle, which is made up of two electrons, it has a total spin, which is either 0 or 1, because you either just add or subtract the spins of the component electrons. And so what happens is that by the pairing mechanism of these electrons, you get a composite particle that is a boson. Okay, and so these paired electrons act like bosons. And once the temperature gets low enough, those paired electron boson things can Bose-Einstein condense, and it is that Bose-Einstein condensation that leads to superconductivity. All right, so now how does this work? So it turns out it's actually relatively easy to understand. All right, so you've got, again, so what happens is you've got a block of material, okay, and that block of material, again, you can imagine the atoms in it are arranged in some crystalline lattice, like we talked about the last time, okay? So let's imagine that we've got the nuclei of our atoms arranged in a crystalline lattice, like so. What the hell? Okay, so there we go. And I'll do one more row just to make things nice and neat here. Okay, now again, what these little dots represent are the nuclei of the atoms that make up our conductor. All right, and so now nuclei are composed of neutrons and protons, and hence they are positively charged. So these little blue dots have positive charges on them. Now, well, I should use red. Now, this thing, before it hits, let's say, this critical temperature for the onset of superconductivity, let's say, it's still going to act like a conductor, all right? And conductors, like the classical model of a conductor that you guys learn in like physics, what is it, like 2B or 40B or whatever the hell they call it here, the general idea you should have in your head of a conductor is essentially this array of stationary positive nuclei, among which the electrons are essentially floating around more or less freely. Okay, so it's not that the electrons are specifically bound to any one nucleus. They're moving around within this array, and they do so more or less freely. Freely. Now, as they move around, they can, collide with these nuclei, and these collisions are essentially what lead to the phenomenon of resistance. Okay, so it's like the chips falling down the Plinko board in The Price is Right. As they bounce around inside this array, they hit things, and that opposes their motion, and it's that opposition to motion that manifests itself as resistance. Okay, so what we've got is a bunch of little red dots flying around inside our lattice. And now the key point here is that these are all electrons, and electrons are all negatively charged. Okay, so that is another reason why you might say to yourself, Professor Kuhlman, you're out of your damn mind. Electrons are not going to pair up with one another. They're both negatively charged. And if you try to pair them up, they're going to say, no, get the hell away from me. I don't like you. You're negatively charged. I'm negatively charged. It just isn't going to work out. Okay. But, so now it turns out that even though the electrons are all negatively charged and consequently repel one another electrostatically, by essentially submerging them in this sea of positively charged nuclei that make up the crystalline lattice, that gives them a way to talk to one another. All right, so now let me undo all my hard work and erase all of these electrons. And let me just draw one. So let's say I've got an electron right here, and it's, say, flying that way. Okay, so now again, this electron is negatively charged, and these nuclei are positively charged. And now, whereas negatively charged electrons are like, oh, no, 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 you stay away from me. Negative and positive charges, they're best buds, right? So the positively charged atomic nuclei are going to be attracted to the electrons. And what that's going to cause is a deformation in the structure of the crystalline lattice. All right, so what's going to happen is, because of this electrostatic attraction, what's going to happen is, let me draw it. These guys are going to be attracted to my electron. Okay, so it creates a deformation. And as the electron moves this way, then these guys are gonna, so they like squeeze together and then they fall back apart. And then as it moves in this direction, that deformation is going to continue, right? So then these guys are going to come together as the electron comes past. And so what you're doing is you're introducing an excitation into the crystalline lattice. You're essentially introducing vibrations into it. Phonons. So as the electrons pass through the crystalline lattice, they deform the lattice, and those deformations act like waves, that is, the phonons that we talked about last lecture. Okay, so now, so what we've got here is, oh, crap. What we have here is a electron that's getting really uncomfortably chummy with these positively charged atomic nuclei, right? They really like each other. It's kind of uncomfortable sitting here watching them, frankly. And so now what this leads to is you now have more positive, because the positive charges in this lattice have been deformed, and now they're closer together. Then what that means is that in this region of the lattice, you have a higher positive charge density than you have everywhere else, right? Okay, so in this region, it looks more positively charged than elsewhere, simply because the nuclei have gotten closer together because they've been attracted by this electron. Okay, now you put yourselves into the shoes of another electron over here, right? So now this electron over here, again, it's negatively charged, and it sees this juicy, positively charged party going on over here, and it they like that, right? So it's attracted to this deformation, or the phonon, in the crystalline lattice, because again, the phonon corresponds to a local concentration of the amount of positive charge in the lattice. The electron is negatively charged, and so this second electron is electrostatically attracted to the phonon that has been generated by the passage of the first electron. And it's through this indirect interaction of electrons being attracted to the phonons that are generated by other electrons as they pass through the lattice. That's what generates this pairing between electrons. Okay, so now you can imagine that as this first electron, let's say whatever happens to it, that it decides to head up here for whatever reason. Okay, so that essentially the deformation in the lattice is going to follow the path of that electron. And, because the second electron is attracted to that, it's going to follow along with it. So they're going to be paired up as they move through the lattice. And this pairing of electrons is what is referred to as a Cooper pair. Okay, and I believe this is the basis of what's referred to as BCS theory, for Bardeen, Cooper, Schrieffer, I believe. All these guys, I think, were at the University of Illinois, where I was before I came here. It's damn cold in Illinois. Okay, so that's the idea of superconductivity, or at least the BCS theory of low temperature superconductivity, is that. So now you ask, why does it only occur at low temperatures? Well, so the deformation in the crystalline lattice, you can imagine, the nuclei are pretty huge compared to the electrons. So this phononic deformation of the crystalline lattice caused by the electrons is relatively small, right? Because they're so massive, they don't move too much. And so if the temperature is high and all the nuclei are jiggling around anyway from thermal fluctuations, essentially the size of the thermal fluctuations are such that it'll just wipe out any of this very gradual deformation in the crystalline lattice just due to the motion from temperature. So it's only when the temperature gets really low and therefore the random thermal fluctuation motion of the nuclei becomes pretty small that these small deformations generated by the passage of electrons actually becomes significant enough that other electrons in the material can feel it. And it's therefore only at really low temperatures that the BCS theory manifests into superconductivity. It makes a lot of sense, right? I feel like it makes a lot of sense. So now you may know about high temperature superconductivity, and nobody knows what the hell is going on with high temperature superconductivity. You may have heard about what's it called? Twistronics. You can take like 2 sheets of graphene and twist them relative to each other in some subtle fashion, and you get superconductivity. And people are super excited about this because, why the hell does that give you superconductivity? And they're hoping that, by analyzing exactly what's going on in these twistronic systems, that'll give some insight as to what the mechanism is leading to high temperature superconductivity. But it sure as hell ain't this. So, high temperature superconductors are a totally different animal. Nobody understands anything about how they work. And if you figure it out, you get yourself a Nobel Prize. All right. All right, so that's essentially all I wanted to describe for you about superconductivity. So it's the pairing of fermions into composite bosons through this electron-phonon interaction that allows them to behave like bosons and therefore Bose-Einstein condense at low temperatures. And that Bose-Einstein condensation manifests itself as superconductivity. All right, cool, right? Okay, so then let's move on to our next. So that's essentially everything I've got to tell you about quantum gases. And so now we got, like I said, 2.5 weeks left. So somehow we got to entertain ourselves for 2.5 more weeks. Okay, and what we're going to entertain ourselves with is the Ising model. Now I've heard people pronounce this Ising. I've heard people pronounce it easing. I don't know which it is. I'm just going to say Ising because I feel like it sounds better. And so now, like I mentioned last lecture, the Ising model, if you get into research, it's a relatively important thing, because if you are doing research and you're trying to figure out some actual honest to God problem out in the actual honest to God real world, and that problem has something to do with statistical mechanics, so like myself, I encounter this in my own research. The first thing you ask yourself is, how do I make this problem look like a random walk? Because I know everything about random walks, okay? And if that doesn't work, if you can't make your problem look like a random walk, the second thing you ask yourself is, how do I make this problem look like the Ising model? Okay? And you would be amazed at all the different places and applications and problems that you can apply the reasoning behind the Ising model to. So like, for example, in my line of work, first time I encountered it was DNA sequence analysis of all things, right? So you have 2 sequences and you line them up and you try to compare how they're related to one another. And it turns out that if you apply the Ising model to this comparison between DNA sequences, it'll actually tell you some interesting things. I'm not going to bore you with it because I won't elaborate. But DNA sequence analysis, that It's maybe not the first thing you think of when you're thinking about statistical mechanics, but turns out it does have some application. All right, so the Ising model is extraordinarily useful. So let's spend the remainder of the class familiarizing ourselves with the Ising model. So first of all, what is it? So the Ising model is a model for the origin of magnetization in materials as a result of spin. So in other words, the Ising model is the answer to the question of magnets. How do they work? All right. So what the Ising model tries to explain is why do we have magnets? Okay. And so now, so in other words, we're going to be talking a lot about magnets. And so now, first of all, before we get into the hairy, nitty-gritty details of the Ising model, let us first remind ourselves of some of the general properties and description of magnetism in your intro physics class. All right. So first of all, magnetic fields. So magnetic fields arise from moving electrical charges. Fields arise from moving electrical charges. Okay, so specifically, if you imagine, let's say I've got a current loop, right? So up here, I drew my electrons as red, so I'll draw this as red. So let's say I have a loop in which electrons are flowing. Electrons are electrically charged particles. And so, oh, I drew this wrong. I should have drawn it over here to give myself more space. There we go. So because electrons are electrically charged particles and they're moving anytime you generate a current, those moving electrons generate a magnetic field. Specifically, what that magnetic field looks like, let's do purple because I love purple. Just last night, my daughter and I watched some Prince videos on YouTube, so I'm in a purple kind of mood. So the magnetic fields arising from the flow of current through a loop like this winds up looking something like this. There it is. I'm sure you've all seen things like this. I hope you've all seen things like this before. Okay, so there's the magnetic field generated by a current loop. And it turns out that this magnetic field that is generated by a current loop looks exactly like the magnetic field that is generated by a dipole magnet. All right, so if I just have a hunk of material that is magnetic, then this hunk of material is going to have two poles on it. It's going to have a north pole and a south pole. And the magnetic field that this bar magnet generates looks exactly like this magnetic field that our current loop generates. It's what's called a dipole magnetic field. All right, so I'm not going to draw the whole thing again, but it looks more or less identical. Not more or less identical. It is identical. All right, so they're the same thing. Okay, now, just as I did here, and you sat here and you watched me do it, I got tired of drawing all these damn magnetic field lines. So there's an easier way to do this. So anytime you have a dipole magnetic field that looks like this, a much easier way to represent this dipole magnetic field is just with a single vector. All right, so this can be represented. This is represented by a single vector. Okay, and this single vector with which you can represent dipole magnetic fields is the magnetic dipole moment vector called mu. All right, so the way that mu is defined is that if I have a dipole magnet with the north pole up here and the south pole down here that generates a field that looks like this, where the field lines run from south to north, I believe. So north is a field source and south is a field sink. That this dipole magnetic field you can represent simply by just a single vector that points from the north pole to the south pole, called mu. All right, and so this one vector mu represents this dipole magnetic field. And again, the direction of the dipole moment vector points all just by convention from south to north. And its magnitude is related to the strength of the magnetic field that you're talking about. Okay, so that's how, so instead of drawing all these field lines for the remainder of all my drawings, all I'm going to draw is my magnetic dipole moment vector. All right. Now, the next thing we need to talk about is spin. Okay, so all elementary particles have some spin. Okay, now, why? Okay, so the explanation I'm going to now show you is not rigorously correct because particles are not, something like an electron is not literally a ball of charge. Okay, it's a mathematical point as far as we know, and so it has no dimension. Okay, but it still can be a useful model to have in your head of thinking of an electron as a charged ball. Okay, so you can think of an electron, again, it's not correct, but you can think of it like this. It's a ball that's got negative charges spread out all over it. Okay, now what happens if this ball is spinning? Okay, so if the ball is spinning, so let's say it's spinning about some axis that, say, right there. Okay, so it's spinning this way. Then if you look at any point on the surface of the electron, again, it really rubs me the wrong way to say such things, but again, just the simple model we have in our head. You look at a point on the surface of this ball, that point corresponds to some amount of negative charge. And if you watch that point on the ball as the ball rotates, then what you get is that that single point on the ball, rotates through a circle, like so. So in other words, what you have is an element of negative charge that is traveling around in a circle, in a loop, as the ball spins. And so what that means is essentially every point on the surface of this ball is going to act like a current loop. And as a consequence, the spinning of this charged particle generates a magnetic field. All right, so what's going to happen is that this particle, because it is spinning, is going to generate a magnetic field. I'm getting good at that. Okay, and again, I'm going to get tired of drawing it. And so what this means is that each particle that is electrically charged and has some spin is going to have a magnetic field. It's going to behave exactly like a little bar magnet. All right, so an electron acts exactly like a bar magnet. That is, as a consequence of its spin and its electrical charge, it has a magnetic moment, mu. Okay, now, because the charge on the electron is negative, then, you can define a similar vector that describes the particle's spin. So, you wrap your right hand in the direction of the spin, and the direction your thumb points corresponds to the spin vector. So in other words, the spinning electron also has a vector you can define that describes its spin. And because the charge on the electron is negative, the spin vector and the magnetic moment vector are going to point in opposite directions. All right, so if this is the magnetic moment vector, that means that the spin vector would be pointing this way if we were to draw it. And we're not really going to talk about this vector very much. It's just something to remember, right? This thing's negatively charged. Usually currents are defined in terms of positive charges for God knows what reason. And consequently, because electrons negatively charged, two things are going to point in opposite directions. Okay, so electrons act like little bar magnets. Those bar magnets can be represented by a magnetic dipole moment vector that describes the orientation of the magnetic field that the electron generates as a consequence of its spin. Okay, now the next thing that we have to remember is what happens to a bar magnet when you put it into a magnetic field. All right, so again, let's imagine we have a bar magnet, whatever that is. So it could be an electron, it could be a current loop, it could be an actual literal honest to God bar magnet, whatever it is, just something that's generating a dipole magnetic field. So here it is. So here's my dipole magnetic field. And I put this bar magnet, or I put this dipole into an external magnetic field. So I'm going to have another magnetic field. Let's say it's this one. So this is B external. All right, now, I mean, you guys have all done this before. You get two magnets, you bring them close to one another, and they're either attracted or repelled from or to one another. And what's causing that attraction or repulsion is the bar magnet interacting with the magnetic field coming off of the other bar magnet. So what's happening is that you have one bar magnet over here that's generating a magnetic field in the space around it. You put another magnetic dipole into that field, and that makes that dipole want to reorient relative to the field. Okay, specifically what happens is you put a dipole into a field and it's going to feel a torque. All right, and again, you have learned this before. The torque that a dipole feels when you put it in an external magnetic field is equal to mu cross B. Okay, or you can write the magnitude of this torque is mu B sine theta, where theta is the angle between the magnetic field and the dipole moment vector. And so, in other words, if this angle is anything other than sine of 0 is 0, right? Yes, sine of 0 is 0. So if this angle is anything other than 0 or 180, you're going to feel a torque. Okay, so in other words, and then so your field torque that causes the dipole to rotate, because that's what a torque does. And it rotates until it don't feel no more torque. And as we just described, you don't get any more torque once that angle is 0 or 180 degrees. So in other words, what's going to happen is that the dipole reorients itself in the direction of the magnetic field. Okay, now why do you say in the direction of instead of in the opposite direction of? And that's because you can also associate a potential energy with this interaction. Okay, so there's a potential energy that characterizes this interaction between a magnetic field and a magnetic dipole moment. And this potential energy is a function of the angle between the magnetic dipole and the external field. And it is equal to minus mu dot B. Okay, and again, you guys know this. Again, you can write this in terms of scalars. It's mu B cosine theta. So if theta is 0 degrees, you get -1, and this number comes out to be negative. That is a low energy state. If theta is 180 degrees, then cosine of 180 degrees gives you -1. Okay, so if this, and then, so this would come out to be -1 -1 times this negative out front would give you a positive number, and consequently, that is a high energy state. So when the dipole moment orients along the field, I guess I should use the pointy end, aligning along the field, that is the lowest possible energy state. And when it aligns anti-parallel to the field, that is a high energy state. Okay, does that make sense? Okay, and in particular, the difference in potential energy between the, let's not write like that, difference between the parallel and anti-parallel states is just, you can just see it from this, it's just 2 mu b, right? Because if it's oriented, it goes down by mu b, right? And if it's anti, it goes up by mu b, and so the difference between those two is 2 mu b. All right. Okay, so the things to remember here is that this is the energy difference between parallel and anti-parallel orientations. And that arises as a consequence of this potential energy between a magnetic dipole moment and an external magnetic field. And that is coming from this torque that the magnetic field exerts on the magnetic dipole moment that is inside of it. All right. Cool? Cool. All right, so now that's essentially all the background information we need to know about magnets in order to understand the Ising model. Okay, so again, the Ising model, the idea behind it is to try to explain the magnetization of a piece of material. Okay, so in other words, I got a bar magnet, that bar magnet puts off a magnetic field. Why? How indeed do magnets work? Okay, so in other words, what we're talking about are solid materials that are generating magnetic fields. And as we've done when we talked about solid materials previously, we are going to imagine those solid materials as a regular crystalline lattice. All right, so let's imagine our material, whatever material we're talking about. We're going to draw it like this. It's just a regular lattice. And now it turns out that most of the magnetic field that is generated by a magnet is coming actually from the spin of the electrons. So here when I draw this grid, what I'm actually referring to is a collection of electrons, all right? So whereas previously what we talked about, those points corresponded to the nuclei that make up the material, here what I'm talking about is the electrons. Okay, now, each of these electrons in this grid is going to have a spin, and that spin is going to generate a magnetic field. Okay, so each of these points, I can associate with it a magnetic dipole moment vector. So let me draw it bigger so it's easier to see. So with each of these points, we are going to associate a dipole moment vector like this. So on and so forth. Okay, now what's happening here? So again, each of these dipole moments is acting like a bar magnet, that it is generating a magnetic field within this material. So for example, this first electron here is generating a magnetic field that say looks like this. Oh, look, this second electron here, this electron is inside the magnetic field that's being generated by the first one. And hence there's going to be some interaction between the dipole moment vector of this electron with the magnetic field that is arising from the magnetic dipole moment of the first electron, and vice versa. All right, so all these electrons are their spins, and therefore their magnetic fields, their magnetic dipole moments are going to interact with one another. Okay, and the net result of that interaction is that they're going to exert torques and forces on each other that tries to drive alignment or misalignment of these magnetic dipole moment vectors. Make sense? Okay, cool. So now here what I've drawn is a two-dimensional array of electrons. 2 dimensions is kind of hard, right? So let's start out simple. Let's start out in 1 dimension. So in 1 dimension, the kind of array that we're talking about is just going to be a line. And on that line, we are going to place at regular intervals electrons. And again, each one of these electrons is going to have some spin and therefore magnetic dipole moment. And our job essentially is to figure out what is the average magnetic moment of this material, right? Because if what winds up happening is all the electrons interact with one another in such a way that all of their dipole moments align in the same direction, then the magnetic fields from all those individual electrons are going to add up, and you are going to get a big net magnetic field, and that, my friends, is how magnets work. It's just from the alignment of the spins and therefore the magnetic dipole moments of the constituent electrons. If they are not aligned, or if they're anti-aligned, then essentially all the magnetic fields cancel out, and then it acts, just like everything else that isn't a magnet. Okay, there is no net magnetic field, and it just acts like a lump of poop. Okay, so that's our job, is essentially to figure out what is the average direction and orientation of the magnetic dipole moments. And from that, we can determine what is the net magnetic field that this material is putting off. Okay, so this one-dimensional array that I've just drawn here, what we can do is label each one of these sites with an index. So I'm going to call that index I. Okay, so this is I equals 1, I equals 2, I equals 3, so on and so forth. Okay, now what happens at the ends depends upon your boundary conditions for the specific problem you're working in. So you can imagine this thing is wrapped around in a loop such that there are no ends, and those are periodic boundary conditions. You could imagine the line is infinite extent, so there are no ends. That would be another kind of boundary condition. So exactly what happens at the ends, we will have to specify each time we work through this problem. Okay, so we're going to have each particle is labeled by N, and we are going to have, no, it's labeled by I, and we are going to have N particles. Okay. Along with each particle, we are going to associate a variable. Which I will call sigma I, which corresponds to the spin orientation of the ith state in this lattice. So this sigma I can be either equal to +1 if the spin is up, or -1 if the spin is down. Okay, so for example, here this first one, this would be sigma 1 equals +1, and this is sigma 2 equals -1. Sigma 3 is +1, so on and so forth. Okay, so this is our random variable that we are associating with the orientation of the spin of each lattice site. Okay, so now the next thing we're going to do is to take this whole material and stick it in a magnetic field. So in general, we can also have some external magnetic field being applied to this thing. So I will call that B. All right, and now our job is, so now what we want to do is, again, figure out what is the average orientation of the spins and therefore the magnetic dipole moments. Okay, the way we're going to do that is statistical mechanics, right? And as we've learned throughout the entire quarter, the most important variable in statistical mechanics describing your system is its energy, or its Hamiltonian, right? So once you know the energy of a given state, you just take the exponential of that energy times beta, and that is proportional to the probability to observe it in that particular state. And so our next job is to figure out what is the energy or the Hamiltonian of this system. Okay, so what is the Ising Hamiltonian? Okay, so you can see that the energy, the interaction energy is going to come from two sources. So if I talk about the energy of, let's focus on this state right here, this site in my lattice. The energy of that lattice site is going to come from two places. One is from the interaction between the specific lattice site and the applied external magnetic field. And the other is going to come from the interactions of the spins with one another. All right, so when I write down my Ising Hamiltonian, it's going to have essentially two terms. Okay, so the first term is going to be electron-electron interactions. And the second term is going to be electron magnetic field interactions. Okay. All right, so now what's going to happen? So what's going to happen is exactly this. Okay, so each spin puts off a field. That field is going to interact with the adjacent spins. And so I'm going to get some contribution to the potential energy that looks like a dot product between adjacent spins. Okay, so that's going to be what the first term looks like, is I'm going to get something that looks like sigma I dot sigma j, right? And then the second term, same thing, right? I mean, it's still an interaction of the magnet. In fact, it's even more explicitly like this, because it's a magnetic dipole moment that corresponds to the magnetic dipole moment of the site that you're talking about interacting with the external magnetic field. So you're going to get another term that looks like sigma I dot B. Okay, and then you have to, for the total energy of the system, you have to add up all of those interactions among all of those sites. Okay, and so the total Hamiltonian is going to be, I just add up all of the possible sites. Oh, I shouldn't have done this. So let me write it out again. Okay, so I'm going to have interactions between spin I and spin j. Now, this here, this is not two spins, right? It's a spin interacting with a magnetic field. So in other words, I've got some funky units going on. And in order to make the units of this term come out, I'm going to just multiply by some fudge factor, essentially, to take care of the units. And so this fudge factor is going to be a matrix that I call Jij. And then I have to sum over all ij. And again, I've got a minus sign right here. So I'm going to put a minus sign right there, too. And then the second term is the spin interacting with the magnetic field, the external magnetic field. So I get that. And again, I have to sum over all lattice sites. And again, I've got a minus sign because there's a minus sign right here. And so, let's see, this is, oh, I'm sorry. It's not like this. It's mu dot B. And then again, I can write this as sum over I j jij sigma I dot sigma j. And then the second term I will write as mu, which is just the magnitude of the magnetic dipole moment vector times the magnetic field, summed over all of the spins. All right, so this is our Ising Hamiltonian. And now we're out of time. Okay, so there's the Hamiltonian, and what we're going to do next time is we're going to start taking this Hamiltonian and sticking it in some exponentials in order to figure out how this system behaves in a statistical fashion. That is, we're going to calculate things like average spin orientations and therefore average magnetizations, yada, 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 yada. All right? All right, so does anybody have any questions? No, you don't. Very good. So then in that case, have a lovely evening. And I will see, today's Wednesday, so next time I'll see you is on Friday. Hasta la vista. This has been a very golden experience. I completely agree with you. It has been enriching for one and all. Have a good day.